Welcome everybody to the panel on the big picture. Okay, it is my absolute pleasure to introduce Sean Carroll. Sean Carroll is a professor of physics at the world's greatest university. So Sean has done a tremendous amount of work on really a variety of subfields of physics, including general relativity, quantum mechanics, the interpretation of how those two pillars of modern physics kind of join together. More recently, he has been interested in the very fundamental question of why does time march forward and not backwards? It's a very non-obvious problem if you really think about it. And what's remarkable about Sean, of course, is that he, in addition to having his academic career in which he has been very productive and prolific, he's also an expert at explaining exceedingly complex things at a level which everybody can understand. So he's unique in this capacity of combining his kind of cutting-edge academic research and his ability to write books at a level which is exciting and informative. So without further ado, let's welcome Sean.
Thanks, Konstantin. So as advertised, I would like to talk about the fundamental nature of reality and the meaning of life. Good, because whenever you say that, there are nervous giggles in the audience. And so part of my mission is to make you question why you giggle nervously when I say that. I think that it's kind of a shame that we don't talk more about the fundamental nature of reality and the meaning of life. The sad news is I'm not going to tell you what the meaning of life is. What I will tell you is some things that we know about life from knowing the fundamental laws of nature, and I will leave it to you to draw some conclusions for what that means about how to live. So I want to start extremely basic. The nature of things moving in the universe, right? Motion and change, how things happen. And this is stuff that would have been bread and butter work for Aristotle and Plato and 2,500 years ago with the birth of modern science and philosophy. But we know more than they did. So there is what the philosopher Wilfrid Sellars called the manifest image of the world. The image we have from our everyday experience, but then there's the scientific image of the world that we learn from science, and there's a gap between these that we would like to bridge. Nowhere is that gap more obvious than in the nature of motion. So what Aristotle will tell you is if you want something to move, you have to push it. Here's an example. The car doesn't move all by itself, even if there's an adorable little puppy driving it, as you might see in the picture. The car goes because something happens. So Aristotle says this is a law of nature. This is how things are. If you're not pushing, it's not going to move. Nowadays, we know better. We know that you can send a spacecraft into outer space and set it going, and it will continue on, a thing called conservation of momentum. This is a very straightforward thing to, torture our physics undergraduates with, solving problems about billiard balls and so forth. But it's also an absolutely fundamental shift in how we think about the nature of reality. In Aristotle's picture, if you see things moving, there has to be a mover. There has to be a cause bringing this into effect. In this picture, what you might call the Galilean picture of the universe or a Newtonian picture of the universe, motion by itself is natural. Things will keep moving until you stop them. That is an important shift in how we think about how things happen. It goes from attaching kind of an anthropomorphic sense of causes and pushers to a more mechanistic sense of things just naturally move through the universe. And this reached its apotheosis in Isaac Newton and his laws of nature. Even Isaac Newton himself didn't quite appreciate how deep the implications of his theory was, the theory of classical mechanics. So if you ever took a physics course as an undergraduate, you might have been asked to take two billiard balls, push them together at some angle and some position, and calculate how they will scatter off, right? It's a typical physics problem. It was around the year 1800 that a French mathematician, Pierre-Simon Laplace, realized that there was something very, very deep going on here. Because usually, we tell you what the condition of the balls are at the beginning, and we say, find out what they are at the end. But Laplace says, if we know Newton's laws, I could tell you what the balls are doing at the end, and you could figure out what they were doing at the beginning. And the point is that it's not there is an effect that follows a cause. That's not how Newtonian physics works. Indeed, it is not how the laws of physics have worked ever since Isaac Newton, whether you're quantum mechanics or general relativity or superstring theory. Instead, there is a pattern that is obeyed. There's something called conservation of information. I could tell you what these billiard balls are doing at any one moment in time, and Laplace says, from that, I can figure out what they were doing at any previous moment, what they will be doing at any subsequent moment. It's not to say that all chaos is broken loose. There's a very, very rigid pattern, but it's a pattern. It's not a push. It's not something anthropomorphic, some personal thing making things happen. Things happen by themselves. Of course, we now know much more about the laws of physics than Newton did. Here are the laws of physics in cartoon form. This is a modern version of the laws of physics in what you might call, what we do call, the core theory, the theory of particles and forces, both subatomic particles and also the gravitational force that we know and love. So here's an atom. You might recognize the cartoon picture of an atom, little green particle. Far away there is an electron. I had a laser pointer at some point. Inside is the nucleus of the atom, and the nucleus is made of protons and neutrons. And inside the protons and neutrons, science, turn it on first. Off, on. Okay, good. Yep. Inside the protons and neutrons, I'm a theoretical physicist, okay? I don't do this applied stuff. There are quarks and gluons, and they're held together by the strong nuclear force. The electron is held together to the proton by the electromagnetic force. There's a weak nuclear force that spits out neutrinos when quarks convert back and forth to each other. And there's gravity. Gravity pulling everything on everything else. And finally, notice that there's a colored background here. That's because there's something called the Higgs boson. The Higgs boson is a field that pervades all of space. It was the final piece of this puzzle that we discovered back in the year 2012. And the dramatic claim I would like to make is that this picture represents the known laws of physics, and that the laws of physics underlying our everyday lives are completely 100% understood. So this is not to say that all of the laws of physics are understood. There's plenty that we don't know. We don't know what happens inside a black hole. We don't know what happened at the Big Bang or dark matter or dark energy. We don't know how to take these fundamental building blocks of particles and put them together in whatever combination we want. We don't know how to build superconductors at room temperature and so forth and so on. But the fundamental rules are known. It's the difference between knowing the rules of chess, knowing how the pieces move around the board, and being a grandmaster at chess, okay? We know the rules. That doesn't mean that we're any good at playing the game. So some of you will say, looking at a picture like this, I don't believe you. I don't believe claims about fundamental physics that are expressed in the form of cartoons. I only believe it if you show me an equation. So there's the equation that you're all looking for. I would like to thank Kent Presents for giving me the 6 hours to explain all the terms in this equation. But basically, there is one equation that is the equivalent of what Laplace said that Newton told you how to do. This is the equation that says, you tell me what the universe is doing at any one moment of time. I will tell you what it will do in the future, what it was doing in the past. And you see all the different pieces of known physics in there. The dramatic part of the claim is not that we know something about physics, but that even as we learn more and more about physics, the more and more that we learn will not affect how we think about human beings. I mean literal human beings, the biological organisms that we are going through the day. We are made of protons and neutrons and electrons. We are never going to find new particles or new forces that have an effect on human biology or psychology. Now that is another dramatic claim that you shouldn't believe it just because I tell you. There needs to be science behind it. So here's the science behind it. It's very sketchy. There's not a lot of words. That's okay. This is a Fineman diagram named after Richard Feynman. My claim to fame at Caltech, the world's greatest university, even though it's not even a university, it's an institute of technology. But I sit at Richard Feynman's old desk at Caltech. And people ask why I got that honor. And the answer is that the desk goes to the most senior theoretical physicist at Caltech who is not senior enough to deserve a brand new desk when they get there. And this Fineman diagram is one of Feynman's greatest contributions. He says this is a way of thinking about the fundamental interactions that particles can undergo. So basically, reading from left to right, as time goes on, you have some particle you know and love, like an electron, and you're imagining there's some new hypothetical particle, maybe a particle that plays a role in human consciousness, right? Wouldn't that be awesome? So Feynman says, well, if that new particle affects the old particle, that means they have to interact somehow, and there's some strength to that interaction. And furthermore, there's a wonderful feature of particle physics that says if this happens, new particle, old particle interacting, scattering off of each other as time goes from left to right, there's another picture that consists of taking this diagram and rotating it clockwise by 90 degrees, and that picture also happens with the same likelihood. So this picture says two ordinary particles come together, they annihilate, and they convert into these new particles that you're hypothesizing. This is how we find new particles. The point is that to find things that we haven't yet found, all you have to do is smash together things we already have found. And the good news is that smashing particles together is experimental physicists' favorite pastime. We do this all the time. This is how we discovered the top quark, the Higgs boson, and so forth. And the point is, we've smashed many, many particles together, all the ones we know about in all the different ways. If there were new particles or forces out there to be found, that would have an effect on our everyday lives. We would have found them already. There probably are new particles and forces out there, but either they're so heavy you can't make them, or they're so short-lived we don't even notice. Whatever you and I are, and obviously there's a lot of mysteries about biology and neuroscience and psychology, we know what we're made of. And that matters. It matters that we know the fundamental stuff of which we are made. That's the easy part. Physics is the great subject to go into if you have a short attention span. There's actually not that many things going on in physics compared to the rest of the world, right? So the picture that we have in mind is there is microscopic fundamental physics. We don't understand all of that, but I'm claiming that we understand the part of that that makes up you and me. Then there's also the process of emergence, the way that these microscopic pieces come together to make the macroscopic world. When we talk about human beings as biology, as agents, as people making choices and doing things that are right and wrong, these are all things that are a higher level description. And our task is to match that higher level description onto the micro world which we do understand. So let me tell you two crucial ingredients in doing that matching. One of them is entropy. The fact that, as Konstantin mentioned, the past is different from the future. You were younger once, you will be older, and we were all younger in the same direction of time. We all remember the past, and we predict the future. It's a very different thing. Why is that true? Physicists will tell you because entropy is increasing over time. Entropy being a measure of the messiness, the disorderliness of stuff. If you take cream and coffee, if these were three different pictures taken at three different moments of time, you would all know which was first, which was second, which was third. The early one is when the cream and coffee are separate, orderly, low entropy. As you mix them together, the entropy goes up. The claim, which is a whole other talk that I'm not giving here, is that this fact that entropy increases is the reason why the past seems to us to be so different from the future. So here's one example of that. I said you remember the past and not the future. Why is that? You have some information right here, right now about the present moment in your memories, in your view, etc. That's not perfect information. You don't see all the atoms and molecules of which we are made. Just the laws of physics would tell you that there's a number of things that could happen in the future and a number of pasts you could have come from, and those are equal in number. We shouldn't have any different epistemic access to the past and future. The difference is that we also know that in the far past, 14 billion years ago at the Big Bang, the universe was very orderly. It was a low entropy state. Why was the early universe orderly? Nobody knows that. That's full employment for professional cosmologists such as myself, but it's true. And knowing that means there are very far fewer plausible pasts from which we could have come than plausible futures into which we can go. That is the fundamental origin of the asymmetry, of the imbalance between how we think about the past as something that is fixed and already happened, and how we think about the future as something that is yet to occur and is more or less up for grabs, something about which we can make choices. So that's one of the big ideas, the idea that entropy is increasing. The other big idea, we can refer to the same picture again, is that there's a difference between orderly versus disorderly and simple versus complex. On the left, this is an orderly picture, all the cream on top, all the coffee on the bottom. On the right, it's disorderly, everything mixed together. But think about how complex these different situations are. On the left, it's very simple, all the cream on top, all the coffee on bottom. On the right, it's also very simple, everything's mixed together. It's in the middle, not when entropy is low or high, but while entropy is going up, that things become complex, that you see the tendrils of cream and coffee intermingling with each other in complicated, intricate fractal patterns. Complexity is something that arises on the journey from simple, orderly, low entropy to simple, disorderly, high entropy. This is not just cups of coffee. The universe does the same thing. Many cosmologists will give you talks about the universe and act like the only important part of the universe is in the past. The future also matters. There's a lot more future to the universe than there is past. Here is a photograph that is taken of the universe 1 second after the Big Bang. It's not really a photograph. It's a white rectangle that I made in PowerPoint, and I tilted it like that. The point is we know what the universe looked like 1 second after the Big Bang, even if we don't have photographs of it. It was the same everywhere, and it was glowing really brightly, thus a white rectangle. As time goes on, what happens is tiny, tiny variations in the amount of stuff in the universe from place to place grow with time because gravity pulls them together. So we get galaxies and planets and stars. But as time goes on, the stars are going to burn out. The galaxies are going to evaporate. A long time in the future, 10 to the 100 years from now, it will be empty space. Nothing around, cold, desolate nothingness. It might recollapse again, we have to think about that, but the betting odds are the universe is just going to expand and fizzle out and be like that for all of eternity. Sorry. The important point is we live here in the middle. We live in the exciting, go-go, fun part of the history of the universe when complex structures can exist, complex structures like you and me. This is why there is something called life here on Earth, because life is the quintessential complex structure. It arises not despite the fact that entropy is increasing, but because entropy is increasing over time. This is an image of the Lost City hydrothermal vent on the bottom of the Atlantic Ocean. This is one of the plausible places where conditions are similar to what we might expect at the origin of life here on Earth. There are low entropy environments that have the property that you can't increase the entropy as you would like to through any simple reaction chemically, but you can increase it through a complex series of reactions. So the hypothesis is that the complexity of what you and I call metabolism, the way that we get energy from our environment, came about because in some, again, anthropomorphic sense, stuff in the early Earth was trying its best to increase entropy, and the only way it could do it was by creating something called life. And of course, once life starts existing, life is a complex chemical reaction that can sustain itself, carry information about itself, procreate, recreate, and then evolve, right? So here we are today, and we are leeching off of the fact that the universe around us is very, very low entropy. We get energy from the sun, right? That sounds important. But we give back, the Earth, the biosphere, gives back to the universe the same amount of energy that it gets from the sun. The difference is that for every 1 photon of light we get from the sun, we get visible light. What we give back to the universe is infrared light. 20 photons are radiated back to the universe for every 1 photon we get. And therefore, the entropy of this stuff we get from the sun has gone up by a factor of 20. What we've done with that is we photosynthesize, we've chewed our cud, we eat, we go around, we have conferences, we give talks, and we radiate stuff into the universe. Our capacities, everything we can do, the fact that we can live, the fact that we can sustain ourselves, have thoughts, build things, create things, is all because we're using up this resource of low energy given by the sun being a hot spot in a cold sky. Now, probably many of you in the audience are with me so far. You're like, okay, yeah, I'm made of atoms and I obey the laws of physics, that's fine. Even life, you know, back in the day in the 1800s, you might have thought that life came about by some life force or elan vital, but we know better now. Life is not a substance. It's not a fluid, it's a process. It's a way that ordinary matter comes together under the right circumstances. But you might worry about consciousness, right? About thinking, about what makes you a person. How in the world could consciousness come out of these atoms bumping into each other? Short answer, we don't know. We don't know how the universe started. We don't know how life started. We don't know how consciousness started. But there's no reason to think it is anything other than the mechanistic process of atoms coming together as entropy increases over time. Let me give you just a few tiny signposts along the way. This is a C. elegans nematode. This is a roundworm that biologists love to study. The human brain has, 85 billion neurons in it. We would like to study the human brain, but that sounds hard. A lot of neurons, a lot of connections. We're trying to do that. C. elegans has 302 neurons. We've mapped them all. We have a picture. You can download it on your smartphone. There's an open worm app that you can play with the connectome, as it were, of the C. elegans. And there's a recent paper that came out that claimed that they can identify one of these neurons that has the job that when something pokes the worm, this neuron's job is to distinguish, did I just poke myself or was I poked by the outside world? To tell the difference between endogenous and exogenous forces, if you want to put it in the technical terms. So you might, with a little bit of imagination, think that the evolution of that neuron, number one, it's not that hard. You can see why that would be a good idea from evolutionary perspective. And number two, it's the beginning of self-awareness. It's the first time that a little neural network inside a living being said, well, this is me and that's something else. And then again, once evolution gets a hold of that, you can go nuts. Here's another step along the way. This is Tiktaalik. This is one of the first fish to climb up onto land. A neuroscientist at Northwestern, Malcolm MacIver, has pointed out that if you're a fish under the water, water has an attenuation length. You can't see very far ahead of you, a few meters ahead of you. So if you're swimming around underwater and you're a fish, you're swimming a few meters per second. When you see something for the first time, it's almost on top of you. And therefore, just to survive in that environment, the pressure in your brain, in your decision-making apparatus, is to make a decision right away. Is this food? Is this a foe? Is this, a potential romantic interest? You have to make the decision right away. Whereas, when you climb up onto land, now you can see for miles. And what that means is that there's a new way of thinking that opens up. It's not just new biology, it's new psychology, because you can see something far away and you can stop and think about it. You can say, what should I do? You can contemplate different prospective future choices. If this was the birth of self-awareness, this might be the birth of imagination, of the ability to hold in our brains different possible futures and try to decide between them. Again, no one knows if this is true, okay? What I'm trying to do is not say what the reality is, but show you how the reality might fit in together, all the pieces matching, all the pieces fitting together. Finally, we come to the perfection of creation, the human brain. This is my brain. This is an image of my brain in action, not to scale. My head is not quite that elliptical. But David Popple, neuroscientist at NYU, was kind enough to put me in his MEG machine. This is a magnetoencephalograph. You might have seen these beautiful pictures of the brain from fMRI machines, functional magnetic resonance imaging, where basically you have really good spatial discretion. You can see where things are happening, but it's really bad for time. You can't see when they're happening. And MEG sees the fact that in your brain, if you believe that the brain is made of particles and particles obey the laws of physics, particles move around and charged particles in motion create a magnetic field. So this is literally some sensors on top of my head measuring the tiny little magnetic field created when the charged particles in my brain hop from neuron to neuron. And the blue and the red are the positive north pole and south pole of the magnetic field. So this is sign, as David said, that I definitely have a brain inside my head, and that my brain thinks thoughts. Not very deep thoughts in this case, but there it is. Now, this doesn't convince anybody of anything. You already know you have a brain, right? You already know there are atoms in your brain. But the point is, we are on the track to map the relationship between the thoughts that you think and the physical processes inside your brain. We're nowhere near done that. That's a long-term project. But when you think, this is what is happening. It's not some abstract thing. It's not something that is disembodied, as René Descartes might have believed. It's stuff happening in your brain. We can even take pictures of it now. And I mentioned Descartes. This is a drawing done by Descartes. There's a wonderful story that I tell in my book of Princess Elizabeth of Bohemia, who was a correspondent of Descartes. And Descartes had this wonderful idea that the mind and body are separate. And Princess Elizabeth said, no, that's silly. Come on, how would they talk to each other? She basically invented what modern neuroscientists and philosophers call the interaction problem. If you believe that the mind is something other than the body, how do they interact? So Descartes had a theory. This little eye drop-shaped thing here is the pineal gland, and it's the one thing in your brain that is not split up into two hemispheres. So basically, Descartes said, this must be the radio receiver. The pineal gland must be the way that your brain gets instructions from its disembodied mind. Don't worry, no one believed him back then either. It doesn't really work. The problem is that equation that I showed you for the core theory. Remember with all the Greek letters and stuff like that? If you believe there is a disembodied mind that is something other than the physical stuff of which we are made, that equation must be wrong. There must be some way that this disembodied mind comes in and pushes around the electrons and the atoms in your brain. No one knows how that would happen, probably because it doesn't happen, probably because we are actually made of atoms and electrons, and that's what we are. So let me lay down some bad news about this. The first piece of bad news is we are all going to die. I mean, you knew that. I don't mean like dramatic. I don't mean like, you know, the world is going to end, you know, terrible biological epidemic or ill-considered 3 a.m. tweet leading to nuclear war or something like that. I just mean in the prosaic sense that biological organisms die. This is a wonderful graph you can find online of mammals, from mice up to elephants, plotting their life expectancy versus their heart rate. It turns out that if you're a big mammal, like a whale or an elephant, you live longer, but your heart beats slower. And the effects almost exactly cancel out. In the state of nature in the wild, a mammal lives for about 1.5 billion heartbeats on average. Now, we human beings, we have pasteurized milk, we have Obamacare and so forth. So we live for twice what we should live, right? That means a human being lives for about 3 billion heartbeats on average, and then you die. And if what I told you about particle physics is right, you don't go anywhere when you die. There's no place for your information in your brain to go. Death is just the end. And I say 3 billion heartbeats because 3 billion is a big number, but it's not absurdly big. Heartbeats go by. You've squandered a few thousand of your heartbeats already, just here in this talk, right? Pointing out that we have in our lifespan 3 billion heartbeats brings home the importance of every single one of those heartbeats. And the final picture, one extra piece of bad news before I finally end on the good news. This is the Hubble Ultra Deep Field. This is a photograph. If you took your camera, took it outside, and pointed it at a blank spot on the sky, put open the shutter on a clear night. If your camera is attached to the Hubble Space Telescope, then this is what you will see. You will see that what you thought was a blank spot in the sky is actually alive with galaxies. We live in a universe with roughly 2 trillion galaxies in the observable universe. Every one of these galaxies has hundreds of billions of stars. Most of these stars have planets around them. Every one of these little dots, the tiniest dot there, is a galaxy with billions of stars. And who knows how many civilizations there are in these planets showing pictures of us, wondering what we're up to. And it can be humbling, because we are a very small part of a very, very big universe. That's the other bad news. But here's the good news. We took this picture. We little human beings, we people who live for less than a century with 3 billion heartbeats, just trying to stay alive, we decided to allocate some of our extremely precious resources to just go looking at the universe because we thought it was interesting. This curiosity, this drive to understand, is something that we have been empowered to do in our brief little lifespans, and we're making use of it. And you're here on a Friday afternoon, Friday morning, because you want to learn more about the universe. That's what makes it all worth doing. That's what gives me hope that we little bags of organized mud that we are as human beings can elevate above the fact that we're just made of atoms and molecules to think about things, to create meaning and purpose in our lives, and to really do something with the heartbeats we've been given. Thank you very much.
Wow, when you said this was going to be a talk on meaning of life, I thought it was just going to be 42.
Well, yeah,
be end.
Well,
okay, so on the off chance that there are any questions, now is the time to ask them. Yes, sir.
Just talk, it'll come on.
So fascinating talk, thank you. Can you comment on how do you think about the promise of artificial intelligence and humans' ability to mimic, taking that to the point where a semblance of consciousness and maybe even something that might be thought of as pretty scary could be developed. How do you think about that?
Yeah, well, I think there's sort of countervailing things going on. I think that as someone who believes that human beings are made of atoms obeying the laws of physics, different kinds of collections of atoms obeying the laws of physics can be just as conscious and artificially intelligent as we are, in principle. In practice, I think that we underestimate how hard it will be because, unlike human beings, the intelligences that we design in computers are intelligently designed, right? For a purpose. It's very easy to build a computer program that will play chess or play Go. That's extremely finite in what can happen. The sort of general purpose intelligence that human beings adapted for is much, much harder. And it's not a coincidence that human beings are really bad at, multiplying 20-digit numbers together in our heads. We have the computational capacity to do that. Any little pocket calculator can do that. Your phone can do that, but we can't? That's absurd. And the point is we're optimized to do very, very different things than that. It's going to be hard, but not impossible, to make computers do the same thing.
I'm going to join the ranks of the amazed and yeah, amazing talk. Thank you. So I have a question. We're humans. And then there are animals, and more primitive. So there's a spectrum of primitivity, I guess, or complexity in alive things. So is it simply the number of the neutrons that we have per brain, or is there something about is there an interaction term, or is it simply just well, we have a lot more neurons that are firing different signals in our brain, so we have higher capacity? Like, what distinguishes us from animals?
Good. So it's not just that we have more neurons, but it's also not new physics either. The interesting thing about something like the human brain, so I agree with you, there's a spectrum. Like, one of the lessons of this way of thinking is the difference between humans and animals, or one species or another. These are concepts that we human beings invent to help us order the world. They're not out there in the world all by themselves. We use them for our purposes. But the point is that it's not just that we have more neurons, but how those neurons are organized. And in particular, they're organized in hierarchies. They're organized in networks, where the neurons come together in little pieces, and the little pieces talk to each other, and the bigger pieces talk to each other. And this networkness is how you explain, for example, why all mammals live for about 1.5 billion heartbeats. And I'm optimistic, although we can't do it yet, that ultimately it will explain how we are thinking in abstract terms in ways that my cats don't seem to be able to successfully do.
Okay, we have time for maybe one more question. I think we haven't heard from that side of the room yet. So.
You made the point that we didn't really understand the Big Bang and what caused it. I'd like to ask a sort of derivative question, and that is, you've mentioned these laws of physics that you say are relatively simple, and you've described them quite eloquently. The question is, where did they come from? In other words, is there some source that they derive from? Is it the same area that we simply don't know with respect to the Big Bang that also populates these types of laws of physics? They didn't arise from nothing, or maybe they did, or do we have any idea at all as to where they derive from?
Good. So I'm very glad you asked that, because it gives me a chance to advertise my new podcast, which you can all check out on the internet near you, where I just did an hour-long solo talk about why is there something rather than nothing? Why does the universe exist? Where do the laws of physics come from? Short answer, yes, we don't know. But there's no reason to think that it needs to come from somewhere outside. Everything that we know about physics today leads us to the possibility that the laws of physics and the evolution of the universe are completely self-contained. The question as to why it exists at all, the question as to why it's these laws of physics rather than some others, I suspect the answer is that's just the way it is. I suspect that there's no absolute necessity for it to have been that way. The universe could have been very different, but we're lucky we got the universe we did.
All right. So on this note, let's thank Sean again. And yeah.